looking at the Bohr model and then using a sample calculation that kind of goes along with that Bohr model. So first we want to talk a little bit about what the Bohr model does. What the Bohr model is a very simple model for the hydrogen atom and what's going on with the electron in that hydrogen atom. First thing about the Bohr model is that there are some limitations dealing with the Bohr model. And one of the limitations is that it will only work for single electron things. So we sometimes say the Bohr model for hydrogen. Because it's relatively simple, we're only really able to look at one electron for this. The other thing about the Bohr model is when it starts to describe some of the specific motions of the electron, they don't actually occur as the Bohr model states they do. There's some strengths of the Bohr model, and that's generally what we focus on when we portray the Bohr model, is because the things it does well and correctly, it does really well in a very simple and straightforward way. So it accurately predicts the energies between two different electronic transitions. We're going to do a sample problem that kind of shows that later. It also accurately predicts the energy required to completely remove an electron from an atom. And it's relatively straightforward and simple. So it's something that we can kind of grasp, even though, as we're going to see, electrons are incredibly complicated in terms of what they're doing. This is a relatively simple model to kind of get at what's happening with the electron. So let's go ahead and talk about what the Bohr model really means. So the Bohr model really deals with electron transitions. And what the Bohr model says, and I have a diagram here on the right that we're going to be looking at as well, is that an electron can move to higher energy levels by absorbing energy. And it kind of makes sense. Things are naturally going to tend towards their lowest energy state. To move them into a higher energy state, you have to input some amount of energy. The electron is no different here. So we can move the electron from a low energy state to a high energy state if it will absorb energy. We can also talk about the exact reverse process. Electrons can move to lower energy levels by emitting energy. And what we're going to see is that the form that that energy gets emitted in is as photons. So if we start looking at this diagram on the right, this shows a lot of the electrons moving to lower energy levels. And when they do that, the energy they give off is the form of a photon. And depending upon the specific energy levels that you see, some of them are going to be in the visible region, that'd be the Balmer series, some of them are in the infrared region, and some of them are in the ultraviolet region. But the release of that energy from the electron is going to come in the form of a photon. The diagram also shows you very clearly is that electrons can skip energy levels. So you don't have to go from 1 to 2 to 3 to 4 to 5. You can go directly from 1 to 5. Same thing coming down. You don't have to go 4, 3, 2. You can go directly from 4 to 2. So these things all kind of make sense with what we know about energy. Things try to tend to their lowest energy states. They're in a higher energy state. You have to put in energy to get that thing there. If it goes back to that lower energy state, it has to give off that energy in some form. So those are all things that match what we generally deal with energy. It's this last part that can kind of give us some trouble. And this is the idea that energy levels are quantized. And being we're at the smallest bits of matter, you're seeing the individual states that can exist. When we're dealing with things on the macroscopic level, things on the macroscopic level aren't quantized. We can be anywhere between two different things. There's a continuum. Now we're down so small in terms of energy and the matter that we're dealing with that we're seeing the individual steps that have to be taken. So what this means when we say energy levels are quantized, that means electrons can only absorb or emit energy if it exactly matches the difference between the energy levels. So this is a little bit different than what we're used to seeing. We're used to kind of seeing things on a continuum. So I kind of want to use our diagram to talk about what this means. So what I want you to imagine is, I'm going to do this in red here. What I want you to imagine is we have an electron in this n equals 1 energy level. We expose it to enough energy that we could get it past energy level 2, but not to energy level 3. So we're giving it enough energy that it could get to n equals 2, but not enough to get to n equals 3. But it doesn't exactly match. Now, in our macroscopic world, anytime you have more than what you need, that process can still happen. Our macroscopic world is not quantized like that. But on the electron, now we're down at the smallest bits of matter. These levels are now quantized. So even if I expose the electron to this amount of energy, that is more than enough to get to energy level 2. We would kind of expect it to go to energy level 2. It's got more than what it needs, but that's not what happens. The electron cannot process that energy. It's going to stay at n equals 1. Why? Because the energy it absorbs has to exactly match. It can't be just more than enough. It has to match exactly. The way I kind of want to view this for you in a non-chemical way is this is a very strict exact change only type scenario. So here's what I want you to imagine. You're coming home. You are needing to stop at the grocery store for something. You just want to pick up one thing and then you're off. Real quick. So you go in, you realize, oh man, you forgot your wallet and your credit card at home. But fortunately, in your center console of your car, you have a $20 bill. So you're like, okay, I can still make the purchase I need. So you go in, you grab your item, you bring it up, cashier rings it up. The total with tax comes to $19.95. Whew, you made it. You have $20. So we're used to handing the clerk a $20 bill. We would get our 5 cents change back. That's what we're used to happening. Imagine now, instead, total's $19.95. You hand the clerk that $20 bill, and the clerk says, sorry, exact change only. Well, even if a store had an exact change only rule, what would you do? You're in a hurry. You just want your item. You want to go home. And it's only 5 cents. So you would say, oh, well, don't worry about it. Just keep the change. And in any sort of normal business sense, you could still make that transaction. You would still make that purchase, and that would be fine. Imagine if it was super strict exact change only. That clerk would not sell you that item because your money didn't exactly match. That's the world that the electron is in. In that world where unless something exactly matches, nothing can happen. Having more than enough to get to energy level 2 isn't good enough. You have to exactly match the energy to get to energy level 2. Another way of thinking about it is this is a complete no-go zone between these energy levels. Nothing exists between those energy levels. These are the smallest steps you can actually see. You can't be at n equals 2.5 and then make change to go to n equals 2. That doesn't work here. You have to exactly match the energy. And that's a little bit different than how we operate in a lot of other things. And that's because we're down at the super small submicroscopic world where we're seeing the individual smallest steps the energy and the matter can undergo for these processes. There's an equation that relates these energy levels, and it's delta E, that's what the triangle is, it's capital Greek letter delta, equals negative 2.178 times 10 to the minus 18 joules times 1 over the final energy level squared minus 1 over the initial energy level squared. Remember, the energy levels are these n equals 1, n equals 2, 3, 4, 5, these individual steps that get numbered from lowest energy to higher energy. Let's kind of look at this equation a little bit. N represents the final and the initial energy levels. That triangle, that Greek letter delta, represents a change, a difference. It's not an intrinsic value. It's not the total energy the electron has. Instead, it's a change. How much did the electron change in this process? It can be a positive value. That would represent energy gained. Or it could be a negative value. That would represent energy lost in terms of how much energy the electron gained or lost in that transition. So that's what you're seeing again on the right. If you're kind of looking on the right, if we have an electron in one of these higher energy levels, as it falls down to lower energy levels, as it's falling down, it has to lose energy. This is how much energy it's going to have to lose. Same thing if we were trying to go up in energy. How much exact energy would you have to gain in order to make these transitions happen? That's what this equation is getting at for us, is what is that energy difference between each of these specific energy levels. Let's look at a specific example of using this. So this problem asks us to say, what is the wavelength of the photon of light that is emitted when the electron in the hydrogen atom goes from n equals 5 to n equals 2? Well, where do we start? Well, we're going to start with that equation we just talked about. And you don't need to memorize the equation. I'll give you the equation. I'll give you the constant. Now we're going to start filling in the information that we know. Well, we're looking for this change in energy. This was a constant. This was already here. We have to fill in our energy levels. And final, that's the ending spot, the final spot for the electron. In this transition, it ends at n equals 2. That's its final destination. So I have 1 over 2 squared. Where does it start at? Well, it starts at the n equals 5. So that's where I'm getting this 5 squared in this equation. At this point, it's just a matter of simplifying and combining terms. What I highly, highly recommend as you're going through this is don't leave things in fraction form. Nothing good ever happened when you leave things in fraction form. Please just move those over to decimal form. It'll be much, much easier to do that. So instead of 1 over 2 squared, instead of 1/4 minus 1 over 25, just put it in decimals. 1 over 4 is 0.25. 1 over 5 squared is 1/25 or 0.04. Put those in decimals. That'll be much easier for you to do the calculation. So combining those terms, I'd get 0.21 in there. Multiply that by the 2.17 times 10 to the minus 18. And what we're going to get is our change in energy is going to be negative. That's important. Energy has to be lost in this. We know it has to be lost because we're going from a higher energy level, n equals 5, to a lower energy level, n equals 2. So we would get negative 4.57 times 10 to the minus 19 joules. Remember, small amount. We're dealing with a single electron in a single hydrogen atom. This represents the energy that the electron lost. Now, where did that energy go? That's what we have to talk about next. So we have the energy that the electron lost. The energy that the electron lost goes into the photon of light that's emitted. That means the energy of that photon of light will be 4.57 times 10 to the minus 19 joules. Notice we have no negative sign here in this, because this is the intrinsic or the total energy of that photon. It's not a change like what we saw in the previous equation with the electron. This is the actual energy of that photon. Now that we have the energy of that photon, we can kind of go through the steps of figuring out what the wavelength is. Well, if I have the energy of the photon, I can use E equals h nu. So I have the energy, that's what we calculated from our previous equation. Remember, no negative sign. E equals h nu deals with the photon. This is the intrinsic energy. No positive or negative here. H is a constant that's provided. So what we're missing is the frequency. We can solve for frequency. This equation has 3 pieces to it. We have 2 of those 3 pieces. We just have to solve for that third piece. In order to solve for that third piece, divide both sides by the 6.63 times 10 to the minus 34 joules times seconds. That will isolate the frequency. Frequency will come out to be 6.89 times 10 to the 14 inverse seconds. A big number. Remember, you have a photon of light. Light waves have very high frequencies, so we're expecting a big number to come out of that. Now that we have the frequency, we can work on determining what that wavelength is using C equals lambda nu. Again, this equation would be provided for you. You'd be provided with the constant, which is the speed of light. So you'd have 3 times 10 to the 8th meters per second. The frequency is what we solved in the previous step, 6.89 times 10 to the 14 inverse seconds. What do we have left? Well, the only thing we have left is the wavelength. So in order to solve for the wavelength, we would have to divide both sides by 6.89 times 10 to the 14 in order to isolate the wavelength. When you would do that, the wavelength would come out to be 4.35 times 10 to the minus 7 meters. And that actually ends up being in the visible region of the spectrum. If you would go back a couple slides and kind of look at that chart, you would see 5 to 2, that falls in the visible spectrum. So when we're thinking about the Bohr model, we're really thinking about energy levels. And the key thing in these energy levels is remember that they're quantized. We're not seeing a continuum. We kind of have that strange exact change only rule. We can only absorb or emit in the exact specific quantities that that equation provides for. We no longer have a continuum because now we're at those smallest bits of matter. That's the key things that we're looking at in dealing with the Bohr model and being able to deal with this level of calculation. So it's kind of combining that new equation with the delta E along with these equations in red, E equals h nu, C equals lambda nu. We've seen those before. It's kind of combining that with that previous equation. Remember, a delta is a change, and that's for the electron. That can be positive or negative. When we're dealing with E equals h nu, that is not a delta. That is an intrinsic value. That's that total energy of the photon. So you kind of got to keep in mind, what are you dealing with? The photon or the electron? Which equation is referring to which?